So this first question then tells you that it's a negatively charged student we have here, which tells me that electrons are being transferred. That's what happens with every electrostatic charge. It is a transfer of electrons. Don't talk about transferring protons or anything else. It's electrons. And because it's the student becoming negative, it's a transfer of electrons to the student or from the carpet. So there you have your 2 marks. Then you're asked to complete the diagram for the field lines around the negative charge, and 3 more arrows. So I would draw the one through the middle here and call that 2 arrows. So you've got one coming in from the left and one coming in from the right, and then one coming up from the bottom, and they're all going in like the one you're given. So there's a nice easy 1 mark. Then part C tells you the negatively charged student touches a metal tap and receives an electric shock. The difficulty with this part C is not so much the physics as really seeing what the question's asking for. Just as an aside here, this is the definition of a field line, and you should know that. So the student touches a metal tap and gets a shock. Clearly then there is a flow of charge. There's electrons moving off the student, and the only reason that happens is because there is a potential difference between the student and the tap. So we have a flow of charge, that's electrons of course, and that's because of the potential difference between the student and the tap. And what's happening is that the student is being earthed. So 2 things really are required here: the potential difference and the earthing. So it's a flow of charge because there's a PD between the student and the tap. That is a flow of electrons, and it's being earthed. So the charge on the student is being earthed. Physics isn't difficult, but knowing what to write in this case I think is quite difficult. So we then have part D. Where the carpet has some thin copper wire running through it, and the student is less likely to receive an electric shock, for 2 marks. So the copper wire, copper's a conductor, so there's a mark that's saying something the question doesn't say that's relevant. So the copper wire being a conductor is worth 1 mark. So the charge will not build up on the student because of the conduction of the copper. So the copper is a conductor, carpet has a lower resistance. therefore the charge doesn't build up, or doesn't build up as much. And I think it's important you appreciate that this whole question hangs together. So 1A tells you or asks you, why does friction cause the charge? 1B asks you about the field around the charge. 1C asks you about how the shock occurs. And then D is asking you, in these circumstances, why would there be less of a shock? So see how the question holds together, really. Then we have question 2, draw a circuit diagram for the circuit you used in your investigation to do the practical shown in part B, looking at the relationship between the PD, the length of the wire and the resistance of the wire. So you need to have your wire, you need to have an ammeter to measure the current, you need to have a voltmeter to measure the potential difference, and a power supply, of course. So a battery or a cell, at least, in your circuit. Given the PDs involved in this circuit, you would have to have a battery, because the PDs are greater than 1.5 volts, which would be the PD across a cell. So you draw your battery, an ammeter in series with the battery, a voltmeter in parallel with the wire, and make it a complete circuit. So there's my battery. Here's my ammeter in series with my battery, and my wire, of course, but the wire isn't there yet. I'm going to put my wire in between these two crosses here. And then I need some means of varying the length of the wire that I'm using. So there's some kind of contact at one end at this point, but of course I can move that along to the right, so I step off less of my piece of copper. And then I want a voltmeter in parallel with that, so I measure the PD across the wire. So there's my circuit. There's more than one way of drawing that, but there's a valid circuit with the ammeter and the voltmeter in the right places. So, in part B then, you're applying Ohm's law, V equals IR, making R the subject, R is V over I. So if you correctly divide 4.48 by 3.54 and so on, you get 5 marks. Describe the relationship. Well, if you look at the table, you can see that as the length gets bigger, the resistance gets bigger, so that's worth 1 mark. But if you were to say that the resistance is proportional to the length, that's worth 2 marks. Why is it important to use a low voltage supply? Well, one point is that the mains voltage is not low voltage, and with that higher voltage, higher potential difference, you run the risk of overheating and electric shock. So there's your 3 marks. Overheating, electric shock, because of the much higher mains voltage compared to your low voltage supply. Question 3 then, using figure 1, how can you tell that the temperature of each wire is constant? Well, the graphs are straight lines. The current is proportional to the potential difference. So the resistance is constant, so the temperature is constant, because the temperature would change the resistance. So the fact that they're straight lines for 1 mark is really all you have to say. Which one of the wires ABC has the greatest resistance? Well, you know that resistance is potential difference over current, and the gradient here is the current over the potential difference, and therefore the gradient is 1 over the resistance. So the bigger the resistance, the smaller the gradient. Or vice versa. But in this case, C is the one because it has the smallest gradient, and the gradient is 1 over the resistance. You've got to say both of those things for the mark. And there is no mark for any kind of justification for A or B. You can't just say the current is lower for C. If you're going to do this in words, you've got to say for a particular current, or for any given current, or any given potential difference, the current is smaller. You can see that if you pick any one value of current, any one value of potential difference, the current at that value for C is smaller than it is for A or B. But you can't just say the current is smaller for C, because I could say, well, this current for C is bigger than this current for B, so therefore you're wrong. You might say, well, that's stupid, but however, it is a possible interpretation of what you might have said, that the current is smaller for C. It isn't always, but for any given potential difference, the current through C will be smaller than it is through A or B. So you need to be unambiguous in what you say. Part B then, the units of resistance, ohms, lowercase o, with the symbol omega. Don't put a capital O on your ohms because that's wrong. Part 2 then, which two wires, J, K, L, M, show the resistance of a wire depends on the length. Well, the only thing that can be changing here then is the length. With J and K, it's the same material but different diameters, so that's no good. K and L are the same material and the same diameter, the only difference is the length. So K and L is the answer. And again, if you get it wrong, there are no marks. You can't say L and M and justify it somehow. Unless you say K and L, there is no mark for the justification. Part 3, well, the answer there, of course, is you need to test more types of metal. To say you've only tested 2 is not enough. You've got to test more metals, or more than 2 metals. Question 4 then, explain series and parallel. Series, the same current flows through all the components. Parallel, the current through different components can be different. There is only one loop, only one branch in the circuit for series, and there's more than one loop or branch or path in parallel circuit. So there you have your explanation. Which of these resistances or arrangements has a resistance of 10 ohms? Well, can't be the first one. Second one will be less than 10. Third one is 2 5s in series, that's 10. The fourth one will be less than 5. So it has to be R. That's 20. That's the highest resistance. When you're drawing these symbols, you have to draw them very carefully. Make sure your rectangle is a rectangle. Make sure you've got no gaps between the sides. Make sure the wires come into the ends but not into the rectangle itself. Keep it tidy. Filament lamp, circle with a cross in it. Again, the wires touch the circle, don't go into the circle. And the diode, triangle, vertical line on the apex of the triangle, circle around that, and a line through the middle. make sure you're able to draw these circuit symbols, correctly. If this was my exam, I would go back and clear that up. I wouldn't leave that ragged edge on my rectangle. Question 6, an example of a linear circuit element. Well, that's a resistor. And a non-linear circuit element, that's filament lamp. Diode is also non-linear. And what a non-linear element means is that the current is not proportional to its potential difference. Question 7, a constant resistance as the PD varies, that's a resistor. Can only be. This is a diode, of course, it's the only component that does that. And this would be a filament lamp. Heats up significantly when switched on. That's how it gives out its light. Question 8, because resistance is PD over current, V over I, and the gradient is V over I, then the steeper the graph, the bigger the resistance. Sketching the characteristics then for the filament lamp. You've got to put I on the vertical axis and V on the horizontal axis, because V is your independent variable and I is your dependent. Make sure that you label your axes with the quantities and the units. You know the resistance increases, so you know the gradient decreases, and so it curves like that. You have to put it into the third quadrant as well. So there you go. You should know that graph, but equally you should be able to work it out. The characteristic for a diode then, well, again, this is in two quadrants. Current in milliamps this time, and PD in volts. And nothing happens until about 0.4 volts, and then it starts to conduct really well. And going the other way, if the PD is reversed, it doesn't conduct. That's kind of the point. It has a very high resistance, so it doesn't conduct very much at all. If your negative current axis is in milliamps, that's the way the graph would look, and that's what you're expected to draw. The graph I actually drew for you, I labeled this axis in microamps, and then after a small reverse bias, reverse PD, you get a breakdown voltage and it begins to conduct microamps. So you do get conduction, but not much. So then, question 9. The symbol for the thermistor, of course, is C. One way that the investigation could have been changed to give a wider range of temperatures, well, you could use hotter water to start with, boiling water maybe, so you extend the top end beyond 60 degrees, or you could use ice to cool it down below the 12 degrees that you've got to. Part 2, describe how the current through the thermistor depends on the temperature. Well, as the temperature rises, the current increases. Part 3 then, you're reading off the graph, looking at 40 degrees and reading off the current, nice and straightforward. You get 0.02 amps. Then in part 4 you're using Ohm's law, V equals IR. You're given R, you've just read off the value of the current I, so V equals 0.02 times 250. Nice and straightforward. Five volts. And then finally part 5, what conclusion can you come to? As the temperature decreases, the resistance increases, because as the temperature decreases, the current falls, so the resistance must increase if the PD is constant, which we have already been told that it is.